Hello friends, welcome again for the second lecture on refrigeration cycles. Now in the yesterday's lecture, you have been introduced to the concept of refrigeration and also the need of refrigeration, where we have learned that the objective of refrigeration is not only to lower the temperature of a space than the immediate surrounding, but also to maintain that low temperature. And while it is not very difficult to produce a low temperature zone, but it is much more difficult to maintain that low temperature, because naturally heat always flows from high temperature to low temperature, and therefore from that low temperature space we continuously have to extract the heat and deposit it back to the surrounding. And for that purpose we need some work input according to the second law of thermodynamics, which leads to the concept of the reversed heat engine, which is also the refrigeration or heat pump cycles. Yesterday we have also discussed about the applications of refrigeration, different ways of producing the low temperature zone, and out of which the application of phase change processes has been found to be the most common one. In fact, the other processes that we have discussed all are in practical use to some degree, but the one that is application of the phase change process probably is the most common way of establishing refrigeration. In fact, I should not use probably, because in 90% cases you will find that the refrigeration systems that you are dealing with or you are experiencing is based upon some kind of phase change process, and even there also it is mostly the one that is written here, the vapor compression refrigeration cycle, where we use a vapor to get compressed using a compressor, and it operates between two pressure levels. One is the evaporator pressure and other is the condenser pressure. The most ideal cycle there is the reverse Carnot cycle, which is just opposite to the conventional Carnot cycle. Here the directions have just become opposite, directions of all heat and work transfer and also the direction of each of the processes, we have just reversed them. Accordingly, it is able to extract heat from a low temperature zone, and it is able to let us say the lowest possible temperature that we are talking about here is the evaporator temperature TE, the highest temperature is the condenser temperature TC. So, from that condenser the refrigerant will be able to extract QE amount of energy from the low temperature space, whereas in the condenser the refrigerant will be depositing QC amount of heat to the surrounding, and in between you have the compressor. This is the compression process. Here the purpose of the compressor is to change the pressure level of the refrigerant from the evaporator pressure level to the condenser pressure level, such that the saturation temperature corresponding to the evaporator pressure, that is Psat, or I should write the other way, TE, which is nothing but the saturation temperature corresponding to your evaporator pressure, has to be lower than the target temperature. Similarly, TC, the condenser temperature, which is the saturation pressure corresponding to the condenser pressure, has to be greater than the surrounding temperature. So, the purpose of the compressor is to operate between these two pressure levels, or to change the pressure level of the refrigerant between this PE and PC suitably. Now, while the reverse Carnot cycle is the most ideal reversed heat engine that we can have, giving the best possible performance or best possible COP, but there are several practical problems with it. If we just write the COP for this, we know, we have already derived yesterday that COP for a reverse Carnot cycle will be equal to TE upon TC minus TE. However, the problem with the practical application of the reverse Carnot cycle is with the two isentropic processes. While the two heat transfer processes are isothermal, but they are also isobaric in nature, because both are happening inside the phase change zone, and so achieving them is practice is not very difficult, but it is very difficult to have this compression process starting from a saturated mixture, and also it is very difficult to have the expansion process. Hardly any work output we are going to get if we start with saturated liquid and continuously expand to a very low quality mixture. To eradicate that problem, particularly on the compressor side, often this evaporation process is allowed to continue up to the saturated vapor line, let us say up to point 2 prime. From there we go for the compression process up to the temperature level of TC, which is this, to reach this point 3 prime. Now, having the evaporation process from 1 to 2 prime and then the compression from 2 to 3 prime is again not too much problematic, we can easily get them. However, the problem happens during the condensation process, because if we want to move from this 3 prime towards this point 4, then this 3 prime to 3 part, this part is the most problematic one, because here we are trying to have an isothermal heat transfer while the system is continuously moving to higher pressure zone. So, basically you have to design a compressor which will also act as an isothermal heat exchanger, which is not possible in practice, and for that purpose we move to this cycle, which we have termed as the standard saturated single stage cycle or the SSS cycle. And as we have discussed, if we compare this cycle with the previous one, where the evaporation is continuing, evaporation process is continuing up to the saturated vapor state, then we have one additional part here. Here let me just summarize the two changes that we are having in this SSS cycle compared to the reverse Carnot cycle. One is, here the heat transfer processes are not isothermal, rather our heat transfer processes are isobaric. So, both evaporation and condensation processes are isobaric in nature, and therefore, during the compression the final temperature, this T2 is not Tc, rather it is greater than Tc, where Tc refers to this particular temperature, just being consistent with the notation used for the reverse Carnot cycle, whereas this is our Te. Lowest temperature though remains Te, but highest temperature is higher than Tc now. So, that here this choice of T2 is such that T2 becomes the saturation temperature corresponding to this Pc, rather being Tc being saturation pressure corresponding saturation temp. Here I have written, rather here here we are going back to the notation that is T2 equal to T sat Pc. Because here if we compare the Carnot cycle notation, this particular notation, here we wrote this when our entire process was restricted in the saturation dome, but once we are restricting this in the saturation dome, then this T3 outside the saturation dome, then this T3 prime is greater than Tc, or I should say it is greater than T sat corresponding to Pc, because the final pressure, or rather it will be better to write if we write that the saturation pressure corresponding to T3 prime will be less than Pc. So, we have to move towards a continuously higher pressure zone, which problem is not here. Here the entire heat transfer is taking place at constant pressure. And the second change that we have done, we are not having any turbine, which has been replaced by a valve or a throttling device. So, we are not having any kind of work output during the process 3 to 4, whereas this is a plain throttling process. So, here we are seeing that during the evaporation process, or let me first talk about the condensation process. In the condensation process, this additional amount of heat has to be rejected. So, there is an increase in the total condensation amount of heat loss, whereas during the evaporation process, because of the presence of the throttling, this is the amount of heat transfer that is getting reduced. So, your QE, there is a reduction, and if we call this area to be A2 and call this area to be A1 to be consistent with our notation that we used in the previous lecture, then we have seen that the eta for this cycle, which has been defined as COP for the SSS cycle divided by COP for the Carnot cycle, that was found to be 1 minus A1 divided by QE corresponding to the Carnot cycle divided by 1 plus A1 plus A2 to W in corresponding to the Carnot cycle, the net work input that is I am talking about. So, any increase in A1, A2 will reduce the efficiency of this cycle, and accordingly the COP for this SSS cycle will always be less than the COP for the Carnot cycle. But still this is practically much more relevant or much more possible, because we do not have to deal with any compression during the heat transfer. Here both the heat transfers are taking place at constant pressure, and also we do not have to deal with that problematic turbine expansion, rather we are replacing that with with a throttling valve. Of course, the turbine work output that we could have got from that conceptual reverse Carnot cycle, that we are not getting, but still it is much more doable in practice. And therefore, we use the standard saturated single stage cycle for practical operations. In fact, its use is so common that quite often this is the one that is referred as the vapor compression refrigeration cycle only. So, the TS and also the pH diagram both are shown here. The throttling process being a constant enthalpy process. So, this cycle actually comprises of two constant pressure and one constant enthalpy process, and therefore, it is quite convenient to represent this one on this pH diagram. Now, if we want to analyze this theoretically, then these are the assumptions that we are considering. Here there are 4 components: evaporator, compressor, condenser and throttling valve. We are assuming all of them to be steady state steady flow devices, then no pressure drop and heat leakage from the pipelines. Because all these components will be connected by pipelines, so we are neglecting any kind of pressure drop and heat leakage from the pipelines. And also I should add that we are assuming both the compression process to be isentropic, and we are neglecting any kind of pressure drop that may takes place when the refrigerant passes through that evaporator and condenser. Then heat addition and heat reaction are isobaric and no pressure drop during them, and we are neglecting any changes in kinetic and potential energies. Then if we try to analyze this particular situation now for a thermodynamic for any kind of steady state steady flow process, if we apply the first law of thermodynamics, then we know that Q dot minus W dot will be equal to H E into, for a single inlet single outlet device, it will be the mass flow rate into H E plus half C E square plus Z Z E, where E refers to the exit state, minus H I plus half C I square plus Z Z I, where I refers to the inlet state. And as we are assuming that kinetic and potential energy changes to be negligible, so this reduces to Q dot minus W dot to be equal to m dot into H E minus H I, or small q minus small w to be equal to H E minus H I. So, now let us try to analyze each of the components separately. First, the evaporator. So, for the evaporator, where we are talking about the process 4-to-1, here it is isobaric and there is a heat transfer going on, but as the pressure is not changing during the process, and this being a steady flow process, I hope you remember that for a steady flow process, small w can be written as integral minus V dP from state 1 to state 2, and as there is no pressure change, so this can be equal to 0 in this particular situation. So, this can be written as Q dot E is the amount of heat that has been added to the system, so that is positive, to be equal to m dot into H1 minus H4, or H1 minus H4 to be equal to Q dot E by m dot, and this particular thing is known as specific refrigeration effect. Q dot E is the refrigeration effect, because we are talking about a refrigeration cycle where the amount of heat extracted is the objective. So, Q dot E is our objective, and once we are dividing that by mass flow rate, we are getting the specific refrigeration effect. Now, if we move that to the compressor, for the compressor where our process is 1 to 2, we have assumed this to be isentropic. So, no heat transfer is taking place, rather work is being given to the system. So, let us write this W in to be equal to W C. In that case, W dot C minus of W dot C is the work input given to the system, which is work being done on the system being it is negative, to be equal to m dot into H2 minus H1 that is W dot C is equal to m dot into H2 minus H1, and if there is any heat transfer going on, then we also have to add with this, but we are assuming it to be isentropic, and therefore, this compression work is given as m dot into H2 minus H1. If we just write the terms again from the previous slide, so we have got Q dot E is equal to m dot into H1 minus H4 and W dot C to be equal to m dot into H2 minus H1. Now, we have the condenser. In the condenser, we are having the process 2 to 3. So, and it is again isobaric, so no work transfer, but there is heat transfer. So, Q dot C, and this heat is being rejected by the system, so it is negative, is equal to m dot into H3 minus H2, which gives you Q dot C is equal to m dot into H2 minus H3, and finally, the throttling device, where we are having the process 3 to 4. Now, we are talking about a throttling process during which there is no heat transfer, there is no work transfer, and so we know that throttling being an isenthalpic process, we can directly write H3 is equal to H4. So, with this we have to evaluate the performance of the system in terms of its COP. So, W dot net work input that is given to the system, W dot in, should be equal to W dot compressor minus W dot turbine, which is not present in this case. So, that will become m dot into H2 minus H1. Then your COP becomes your desired output, which is Q dot E, divided by the effort that you have put in to this, which is W dot in net, that is, it becomes now H1 minus H4 divided by H2 minus H1. Here this numerator is the specific refrigeration effect that I have written, and this denominator, it is often called the specific compression work, that is the amount of compressor work that you have to supply per unit mass flow rate. So, just from knowing the knowledge of the enthalpy of these 3 points 1, 2 and 4, we are able to identify the value of the COP from this. And if you want to calculate any of the heat transfer or work transfer, those also are known just from knowledge of this enthalpies. There is another way sometimes we write this, the refrigeration effect Q dot E. If we just repeat this, Q dot E is equal to m dot into H1 minus H4. M dot is the mass flow rate, which remains constant at all the state points for during steady state steady flow operation, and m dot can also be, this being the mass flow rate. So, we can also write this one as the total volume by specific volume at any particular state point into H1 minus H4, and so if we write this one as V1 into H1 minus H4 by specific volume at state point 1, then this bracketed quantity is sometimes called the volume refrigeration effect. So, while the refrigeration effect is represented in terms of kilowatt, this is kilowatt per unit specific volume or tons of refrigeration per unit specific volume. Now, to evaluate the performance of this SSS cycle, let us check the effect of the two end temperatures Tc and Te. So, first let us check the evaporation temperature for constant Tc. From the previous slide we have seen how to calculate the corresponding performance parameter and also the COP. Now, let us check the effect of Te. So, I have plotted the pH diagram for a particular combination of Tc and Te. Let us say initially this is the value of Tc, which remains constant, this is your Te for case 1. Let us now choose another Te for case number 2, Te2, where this Te2 is less than Te1. Now, if we want to plot this cycle, then what we have to write or what we have to do? for when the evaporator temperature is TE2, then this point 4 will get expanded to this point to become some 4 prime. Then your the evaporation process will start from here and proceed up to the saturated vapor line to give the end state as 1 prime, and then we have to go to the final pressure through the compression. So, this being a constant, we have to expand this. Actually, I should not have written this Tc and T this way. It will be better if we write in terms of the pressures. This is the saturation pressure corresponding to Pc, or maybe we can write this one as Psat corresponding to your Tc. This is Psat corresponding to TE1, and the second one is Psat corresponding to TE2, the lower temperature. Now, through compression we have to somehow reach that Psat corresponding to Tc, the same final pressure. So, your compression line may be somewhat like this to reach a final temperature of 2 prime, and from there it will proceed along the constant pressure line to reach the same state point 3. So, 3 of the state points are changing, only one state point, that is point number 3 at the end of condensation, that is remaining the same. So, if we check the effects now, what about the refrigeration effect? Your refrigeration effect, which is given in terms of this Q dot E, just compare the magnitude of the enthalpy change. Point 4 and 4 prime, they are similar because this we are referring to a throttling process, but if we compare 1 prime with 1, definitely you can see 1 prime is getting shifted towards left, that is the enthalpy value there is less than 0.1. So, refrigeration effect decreases for this T2. What about the compression work? Compression work W dot C. Here we are going from a lower pressure level to higher pressure level because the evaporator pressure is has reduced while the final pressure, the condenser pressure has remains the same. So, this will increase, and the combination of these two being COP, which is nothing but Q dot E by W dot C for a throttling related device, this will of course reduce. And another parameter of importance is the highest temperature. So, highest temperature, which is this T2 prime, that is also increasing because of a reduction in the evaporation temperature, which is also not always the desirable thing. The highest temperature associated with the cycle is increasing, refrigeration effect is decreasing, compression work is increasing, leading to a reduction in the overall COP. So, the recommendation is we want our TE to be as high as possible. Now, if we want to check the effect of Tc for a given value of TE, again we have the same pH diagram. Let us identify the states. Here the evaporator side condition is not changing. So, evaporator pressure remains the same, which is this one Psat corresponding to your TE. Let us say this one is your Psat corresponding to Tc1, and we take another pressure for a higher value of condenser temperature, which is Psat corresponding to Tc2. So, for this particular cycle, what will be your condition? Where should be the point 3? If the point 3 has to be saturated liquid, then that point has to be somewhere here. So, your throttling, this is your 3 prime, your throttling process will go to this leading to 4 prime. 4 prime to 1 will remain the same, or at the end point of evaporation, that is 1 will remain same. Now, this 1 to 2 prime, the the compression process has to be extended to this elevated pressure, giving this as 2 prime, and then from there you will be getting this as your condensation process. So, here our Tc2 is greater than Tc1. So, what is the effect? Q dot E in this case, definitely there is a reduction in the amount of heat extracted in the evaporator. So, your Q dot E is decreasing. The compression work, lowest pressure is same, but highest pressure is increasing. So, compression work is also increasing, leading to a reduction in COP, and exit temperature, the compressor exit temperature or the highest temperature of the cycle, the T2 prime, that is also higher compared to the previous case. So, again this is also detrimental, that is quite similar to the reduction in the evaporator temperature and increase in the condenser temperature also has all possible detrimental effects, and therefore, we always want Tc to be as low as possible. But of course, here we are handicapped by the environmental condition. Tc has to be higher than the surrounding temperature, and therefore, the Tc requirement during the winter seasons can be significantly lower than the Tc requirement during the summer season, and therefore, the COP for the same evaporator temperature during the winter season can be much better compared to the summer season. Now, if we have to check out a few numerical examples, but before that let us see what are the minimum quantity of data that with which we can evaluate the performance of such a system. Let us see for the cycle that is given, we are given with the temperatures Te and Tc, we are given with the HFG corresponding to Te and HFG corresponding to Tc, because once we know the Te and Tc and we know the nature of the refrigerant, we can easily get the value of HFG, and we are also aware about the specific heat for both the liquid and the vapor phases. Then what we can do? Of course, we know all the state points, as we know Te and Tc, at least from there we can identify others. So, as we know Te, so we can calculate the evaporator side pressure to be equal to the saturation pressure corresponding to Te, and condenser side pressure to be equal to the saturation pressure corresponding to Tc. Remember, here the Tc refers to the temperature from this point onwards, not over this zone, because temperature is changing from this 2 till the saturation dome, but inside the dome the temperature remains constant. So, we now know the pressures and we can plot these cycles. As we know the pressure, so what else we can identify from this cycle now? As we know the evaporator side condition, we can get the value of H1, where H1 is equal to Hg corresponding to the value of Te. Now, if we do not have any information about the value of Hf at this pressure, then we can choose certain reference. Let us extend this 4 to 1 line towards the saturated liquid side up to a point 1 prime. So, 1 prime corresponds to the saturated liquid point at the evaporation temperature, and let us assume Hf corresponding to T to be equal to 0 kilojoule per kg, and Sf again corresponding to the same T to be equal to 0 kilojoule per kg Kelvin. These are some reference values we are choosing. Any choice of reference will not hamper your calculation, because we are ultimately dealing with the changes in enthalpy and entropy. So, what will be your H1 then? H1 is Hf plus Hfg all at this T level, and as we have set Hf to be equal to 0. So, this will be equal to Hf corresponding to Te, and similarly S1, which should be equal to Sg corresponding to Te. The same way it now becomes Sfg corresponding to Te. So, we know the entropy and enthalpy at state point 1 at compressor inlet. Now, for compressor exit, what we can do? We know S1 equal to S2 for isentropic compression. Now, as this process being isentropic, or so as we are talking about a reversible process, so for any reversible process we know that del Q is equal to T ds, or ds is equal to del Q by T. From there, let us see what we can write. For the compression process we know S1 equal to S2, then if we write say H3 minus H1 prime, that is we are taking this point and this point, then how we can approximate this? if the specific heat for the liquid phase remains constant, this can be approximated as Cp for the liquid into T3 minus T1 prime, that is Cp for the liquid into Tc minus Te. We are assuming the specific heat to be constant and the liquid phase to be incompressible. Then this we can easily do this. Similarly, S3 minus S1 prime, we can approximate this one to be equal to Cp liquid to log of T3 upon T1 prime, that is Cp liquid to log of Tc upon Te. So, as we know the temperatures and as we have set H1 prime and S1 prime to be equal to 0, so from there we know the values of H3 and S3. Now, what we can do for the condensation process? For the condensation process, we know that Q dot C is equal to m dot into H2 minus H3, or Qc is equal to H2 minus H3. Now, H2 minus H3 can be written as H2 minus H2 prime, where 2 prime refers to this particular point, minus plus H2 prime minus H3. Now, for point 3 we know already the values, and what will be H2 prime minus H3? That is nothing but HFG corresponding to Tc. So, this becomes H2 minus H2 prime plus HFG corresponding to Tc. And what is H2 minus H prime? Here we are talking about superheated vapor. So, if we assume superheated vapor to have a constant specific heat, then we can approximate this one to as in terms of Cp, we can approximate this one as Cp for the vapor phase into T2 minus T2 prime plus HFG at Tc, and we know that T2 prime is nothing but the Tc. So, only thing that remains is the point T2 prime, temperature at point 2 prime. Now, how we can get that? We have to temperature at this point number 2, T2. How we can get that? This is the condition that we have to use for that. During the during the compression process, if we assume the vapor to behave as an ideal gas, we can easily use this S1 and S2 with each other, and from there we can identify the value of temperature T2. So, we can see just from the knowledge of these limited data points, still we can evaluate the performance by suitable reference. So, let us now see one complete numerical example, a very simple one. Here we are talking about a refrigeration system which is using R134A as a refrigerant, and it is operating on an ideal vapor compression refrigeration cycle between a condenser and evaporator pressures which are given, refrigerator flow rate is given, and we have to identify several things. So, this is the cycle. Here we are using R134A as a working medium, so we have to use the property table for that, and once we have the corresponding property table available, then we can easily evaluate the performance. Like suppose your evaporator pressure PE is equal to 0.14 megapascal, the lower one, then your H1 will be equal to Hg corresponding to this pressure, which I have noted the value, which is 239.15 kilojoule per kg, and S1 will be equal to Sg corresponding to this PE, which will be equal to 0.94456 kg Kelvin. Now, look at the point number 3. We know Pc is equal to 0.8 megapascal. So, H3 will be equal to Hf corresponding to this Pc, that comes out to be 95.47 kilojoule per kg, and process 3 to 4 being a throttling one, we know that H4 is equal to H3, the same value. So, only one that we have to evaluate is this point number 2. So, we know that S2 is equal to S1 and also P2 is equal to the condenser pressure. Using these two for the superheated vapor table, from there we can identify the value of this H2 to be 275.39. You have already solved enough problem using water as the working medium for such kind of processes. So, you know how to get the values, you just need the R134A table. So, once we have all of them, then we can easily calculate the required parameters. Like if we want to get the cooling rate, Q dot E will be equal to m dot into H1 minus H4, which is going to be in this case 7.18 kilowatt. Then the rate of heat rejection to environment, which is Q dot C, which is m dot into H2 minus H3. So, that will be coming as 9.0 kilowatt. The compressor power requirement, W dot C is equal to m dot into H2 minus H1, and this one also can be written as Q dot C minus Q dot E. Either way you can calculate, in both case you are going to get this one to be 1.81 kilowatt, and if you combine this, your COP, which is Q dot E divided by the compression work, that will be coming something like 3.97. So, for every unit of compression work input, you are going to get about 4 times refrigeration effect for this. So, and I am leaving one task to you. Instead of using a throttling valve, if we are using a turbine here, that is instead of having process 3 to 4, if we are going by process 3 to 4S, where 4S refers to the exit state for the turbine, then you have to repeat the calculation for all these parameters. The only information that you need in this case is the value of H4S. So, the H4S can be calculated as S3 will be equal to S4S. So, the value of S3 you can get from here. S3 should be equal to SF corresponding to the condenser pressure, and as S3 is equal to S4S, from there you have to calculate the quality at point 4S, and from that quality you can get the H4S. Then you can easily repeat the calculation of all these parameters. Only thing I can tell you that the COP for this case will be about 5.07%, which is about 25 to 30% increase in the final value if we are using a turbine instead of throttling device. But as I have mentioned, practically that is very difficult. Now, in a real situation, there can be several irregularities or irreversibilities that can be present in your SSS cycle, just like shown here. Here we can have several things, like the compressor can have isentropic efficiencies, and therefore, instead of starting from point 1, instead of reaching to point 2, we may reach somewhere here, this 2 prime. So, we need to define an isentropic efficiency for the compressor. So, isentropic efficiency for the compressor eta C in this case will be equal to the minimum possible work input requirement, which is following the isentropic process, that is H2 minus H1 divided by the actual work input requirement, which may be H2 prime minus H1. So, here of course, we are talking about the final pressure to be the final temperature pressure level to be the same, and accordingly you can calculate the value of this H2 prime or locate the point 2 prime. We can also have significant amount of pressure losses, like when the refrigerant is moving from the compressor exit and it is reaching the condenser between this point 2 and 3, we may have some amount of pressure loss. Similarly, from condenser to the throttling valve or from throttling valve exit to the evaporator, we can have significant amount of pressure losses. So, all these pressure losses needs to be taken into account while analyzing a real cycle. Just like this example I have here, I am talking about the same refrigerator that I used in the previous exercise, but here the superheated vapor, here my cycle is like this, where the superheated vapor at 0.4A and 10 degree Celsius is entering the compressor. So, at the compressor inlet, our state is not saturated vapor at the superheated vapor. Quite often we want to do this in order to completely avoid any kind of droplet in the compressor. And instead of reaching point 2 point 2s, it is actually reaching point 2 where the conditions are 0.8 megapascal and 50 degree Celsius. The refrigerant is cooled in the condenser to 26 degree Celsius and 0.72 megapascal. Look at this, at the condenser inlet pressure is 8 megapascal or 0.8 megapascal, at the outlet is 0.72 megapascal. So, about 0.08 megapascal, close to 0.8 bar amount of pressure drop that has taken place inside the condenser. And also the condenser exit condition is not of saturated liquid, rather it is subcooled liquid. And that is also sometimes we would like to do to extract some more amount of refrigeration effect from this. And it is throttled to 0.15 MPa, which is this. So, when it passes from the evaporator inlet to the evaporator exit, there is about 0.01 megapascal of pressure loss. Neglecting any heat transfer and pressure loss in the connecting pipes, you have to determine the cooling rate, rate of heat rejection to environment, compressor power requirement and the cycle COP. So, we need to get the values for all the state points 1, 2, 3 and 4, the enthalpy values from the table, and then you can easily identify the required parameters. Again I am giving you the final value, COP for this case will be equal to 3.93. So, COP has decreased marginally, but the Q dot E, that is the evaporation load, or I should say the cooling capacity, that has also come to 7.93 kilowatt. So, that has also changed compared to the previous value. You please do this simple calculation to get these numbers on your own. Now, I would like to talk little bit about 10 minutes on the refrigerants that we commonly use in vapor compression refrigeration cycle. Refrigerants can broadly be of 3 types. The first one is natural refrigerant. Natural refrigerants, there can be several one of course, but I am mentioning about 3 of them. One is ammonia. Ammonia is an age old refrigerant, one of the earliest refrigerant to be used, and that is why it is quite well known characteristic it has. Its normal boiling point is very advantageous, it is minus 35 degree Celsius, so we can easily go to quite low temperatures using ammonia as the working medium, and it has very good thermodynamic properties as well, quite well known and quite decent thermodynamic properties. So, as a refrigerant ammonia has these advantages, but it has that disadvantages also, like ammonia is toxic, ammonia has very bad odor, so not very useful if it gets leaked to the surrounding, and it is reactive, very important point, it is reactive to certain materials, particularly copper, which is used in the heat exchangers in the condensers and evaporators. So, we can't, if we are using ammonia as the refrigerant, we can't use copper like material. Theoretically speaking, any kind of substance which can evaporate can act as a refrigerant, but there are certain refrigerants that we popularly keep on using historically. So, ammonia is the first one of them. Second is the very popular one for the modern times and also for near future, that is carbon dioxide. Again it is very easily available, it is non-toxic, non-flammable, so there is no issue of toxicity like in ammonia. Carbon dioxide has a normal boiling point of minus 55 degrees Celsius, so capable of going to very low temperatures, and it has very favorable thermodynamic properties under certain situations, even better than ammonia or much better than ammonia. But problem with carbon dioxide is its critical temperature is very low. Its critical temperature is only around the order of 32 degrees Celsius. So, it can go through phase change process only below this temperature or well below this temperature. So, in order to achieve phase change with carbon dioxide, your condenser temperature also has to be much lower than this. Similarly, it has very high operating pressure, because the triple point temperature for triple point pressure for carbon dioxide is about 5 bar, the triple point pressure. So, we have to operate at a temperature, at a pressure level above this in order to have the liquid phase of the carbon dioxide. Remember, below the triple point pressure we can't have the liquid phase. So, we have to work above this pressure level. But still carbon dioxide is quite useful, and with recent modifications carbon dioxide is increasingly becoming more popular for large scale refrigeration. One issue with both ammonia and carbon dioxide are their enthalpy of latent heat of evaporation or enthalpy of evaporation is quite high, and therefore they are more suitable for large scale systems. Sulfur dioxide on the contrary is something that is more suitable for small scale system, because it has lesser latent heat of vaporization and therefore gives high mass flow rate. But sulfur dioxide is highly toxic, so it has been used very less in refrigeration industry. We can also use water as one of the natural refrigerant, but water has not very favorable property as refrigerant. Particularly, you know that water freezes at 0 degree Celsius, and therefore we can't use water as the refrigerant when the evaporator temperature is around 0 degree Celsius. Hydrocarbons have also been used a bit. Then okay, sulfur dioxide has another big disadvantage, that when it mixes with water, it can form sulfuric acid, which is highly corrosive. Next kind of refrigerants we have are synthetic refrigerants. Now, synthetic refrigerants, you must have heard the names. There are three kinds of very popular names we use. One is CFC. CFC refers to chlorofluorocarbon. Chlorofluorocarbon, that is, there is chlorine and there is fluorine. We are talking about hydrocarbons only, but there the hydrogen atoms has been replaced in the molecules by chlorine and fluorine atoms. Then we can also have HCFC, that is hydrochlorofluorocarbon, where we have hydrogen also along with chlorine and fluorine in that hydrocarbon. So, it is HCFC, and finally, we can have HFC, where we do not have chlorine at all, it is hydrofluorocarbon. Hydrofluorocarbon talks about the complete removal of chlorine from the molecule, it is only hydrogen and fluorine along with carbon. So, these are synthetic refrigerants. CFCs and HCFCs have been extensively used in domestic refrigerators or also in large scale application, but because of environmental issues, as we shall shortly be seeing, they are gradually being phased out in favor of HCFC and more in favor of HFCs. So, in future we may not be having any refrigeration system running on CFCs and even HCFCs, but more on HFCs and other natural refrigerants. The idea is to remove chlorine based synthetic refrigerants, and that is why CFCs and HCFCs are being phased out. We can also have mixtures, we can have azeotropic or non-azeotropic or zeotropic mixtures that are also used. Now, for selection of refrigerant, there are several properties of the refrigerant that we have to bother about. One kind of properties are thermodynamic and thermophysical properties, and there the first is the saturation pressure levels. So, the evaporator pressure should be as high as possible. As we have seen, the evaporation temperature has to be as high as possible, correspondingly the evaporator pressure also has to be as high as possible, because if the evaporator pressure is high close to atmospheric level, then the problem of air leaking into the evaporator line, that will be much lesser, and leak detection also will be lower, and also higher the pressure, lower is the specific volume of the corresponding gas. So, we have to deal with lesser volume of gas, and so the size of the equipment will be smaller. Then the condenser pressure should be as low as possible. Just the opposite to this, condenser pressure is always higher than evaporator pressure, but higher the pressure, more thicker pipes that we need, and therefore, if the condenser pressure can be kept to some manageable level, we can use much thinner pipes or much thin walled heat exchangers, and also it is much safer to operate. And another advantage is that if the evaporator pressure and condenser pressure is close to each other, then the compression work requirement, that will also keep on coming down, leading to an increase in the efficiency. Another point that is related to the saturation pressure, that is the latent heat of evaporation should be as high as possible. That is very logical, because the higher the latent heat of evaporation, higher will be the amount of energy extracted during the phase change process, particularly at the evaporation side. So, we can have higher amount of cooling capacity. So, higher the latent heat of evaporation, we can have a higher amount of Q dot E. Second point is the specific heat, but before that I have to mention that these 3 points are not compatible with each other. Quite often we have to go for some kind of trade off between the 3 to check which one is more meritorious compared to the other. For specific heat, the specific heat for the vapor should be as high as possible, so that we do not have to go for too much of superheating, whereas specific heat for liquid should be as low as possible, because in the condenser when we go for subcooling, then we can go for a significant temperature change for this liquid, and so throttling temperature change during throttling, that becomes smaller. Ratio of specific heat should be low, because lower the ratio of the specific heat, the less will be the compressor work requirement. So, this is also a very interesting point to remember. Now, the critical temperature Critical temperature of course should be well above the maximum temperature at which we would like to work. Like for carbon dioxide, I have just mentioned that for carbon dioxide critical temperature is so low that under normal atmospheric condition the temperature may be higher than the critical temperature, and therefore carbon dioxide can't be used as a phase change material under normal atmospheric condition. So, critical temperature has to be high. Then there are several smaller points, like the freezing temperature should be as low as possible. One big point with water, because water, big disadvantage with water, water has a freezing temperature which is quite close to what we need in the evaporator, and therefore water can't commonly be used as a refrigerant. Then the sonic velocity should be high to avoid any kind of compressibility effect. High thermal conductivity to have higher degree of heat transfer in the heat exchangers, low viscosity to avoid frictional losses or pressure drops in the pipelines, etc. Second group of properties are the safety and economics based properties. Here the toxicity is very important. Natural refrigerants like ammonia, sulfur dioxide are highly toxic. Synthetic refrigerants like R11, R12, they are non-toxic under normal condition, but when they come in close to some kind of open flame, they produces highly toxic gases. So, we have to be careful while using them. Then flammability, the refrigerant should be non-flammable, at least within the working range, it should not start to burn. The material compatibility is important, like we have talked about the compatibility or non-compatibility of ammonia with copper. Similarly, the material that you are using for your pipeline should be compatible with your refrigerant. Initial and running costs should be manageable, and finally the environmental issues. In terms of environmental issues, we talk about two parameters. One is ODP, ozone depletion potential, other is GWP, global warming potential. Both are highly talked about terms nowadays. Here the global warming potential talks about the effect the refrigerant may have on the environment in increasing the temperature level of the environment. I am not going to the technical detail of how the GWP is calculated, but one information that you can have, that the GWP of carbon dioxide, or I should write the other way, the GWP for carbon dioxide has been arbitrarily set to a value of 1, and based upon which the others or other refrigerants are scaled. Certain refrigerants have significantly high GWP compared to CO2, certain refrigerants may have quite small, like R12, global warming potential of R12, that is of the order of 8000. So, 8000 times higher global warming it will cause compared to carbon dioxide. Whereas, if we talk about global warming potential of an HFC, which is the modern refrigerant, which is R134A, it is about 1500. So, though HFC does not have any kind of chlorine in this, so they do not have any effect on the ozone layer, but that has significantly high global warming potential. Now, I go to the ODP. ODP refers to the ozone depletion potential. For ODP, R11, or I should write the ozone depletion potential for R11 is arbitrarily set to the value of 1, just similar to GWP for carbon dioxide, and everything has been scaled based upon this. Certain refrigerants have much higher ozone depletion potential, certain refrigerants has quite less, like that R134A that we are talking about, which is an HFC, its ozone depletion potential for this R134A is equal to an absolute 0. So, it does not have any effect on the ozone layer, but can have significant global warming potential. The idea of ozone depletion is that when the in presence of UV rays, the ozone can get converted to oxygen, and this particular reaction gets quickened up by the presence of chlorine. So, the kind of refrigerants which has chlorine in their molecular structure, when those refrigerants get released in the surrounding, and when they are able to reach higher atmosphere, then they generally decompose, leaving chlorine open or free chlorine into the surrounding, and that free chlorine can react with the ozone to get it converted back to oxygen, thereby causing a depletion in the ozone concentration in the upper atmosphere. That is what we refer by this ozone depletion potential. Different refrigerant has different kind of ozone depletion potential, and primarily because of this consideration only, the CFCs and HCFCs which has chlorine in their molecule, that is chlorofluorocarbon and hydrochlorofluorocarbon, has been or are being phased out, whereas hydrofluorocarbon does not have any chlorine in their molecular structure. So, their ozone depletion potential is 0, but they still can have significant amount of effect on the global warming. So, this is the way we this is the different parameters we consider while selecting any refrigerant. The next thing that we have to consider is the naming convention of the refrigerant, that R11, R12 etc. I am talking about. But today I have ran out of time. I would like to stop here itself. In the next class I shall be talking about the naming convention, and then I shall be moving to a few other aspects of vapor compression and subsequently the vapor absorption refrigeration system. So, today we have talked about the ideal standard saturated single phase cycle. We have seen how to analyze that using a complete set of data and also in limited data set. Then we have talked about the actual cycle where we can have pressure losses, heat leakages etc. And finally, we have talked about the refrigerants, particularly the different categories of refrigerants and the selection of refrigerants. Naming convention of refrigerant is something that I wanted to talk about, but in the next class I shall be starting from that point onwards. So, till then just revise this lecture, and if you have any query, write back to me. Thank you.